So we've been talking about Brayton cycles. We know that they look a little bit like Rankine cycles, with the difference being that the working fluid is ideal gas. But they're still heat engines, so we still have the same equation that we always do for thermal efficiency of heat engines, where here we have net power divided by heat in. If we're drawing a TS diagram, it looks like this. As we compress isentropically, we add heat, we go through our turbine isentropically, and then we reject heat. If we have this same four-component system, what's interesting when we draw these PV diagrams is that we're adding heat and we're rejecting heat at constant pressure. If we can make the same assumptions that we normally make for open systems, we'll have that the turbine and compressor powers are m dot times H in minus H out, and the heat addition and rejection processes are m dot times H out minus H in. We'll trust the first law to give us the right signs. But then we'll have to ask, what's the fluid? And in this case, the fluid is ideal gas. So we have to remember how to find H or delta H for ideal gases. If it's an air standard or variable specific heat problem, we'll actually find the individual specific enthalpies. If we have an isentropic process, we'll look for an equation where we can use isentropic processes for ideal gases with PR or VR in the equation. Because for Brayton cycles, we're typically using open system processes, we'll use pressure ratios instead of the volume ratios we used for internal combustion engines. Typically, we'd be looking for the reduced pressure at the exit of the isentropic compressor or the isentropic turbine. We'd get that from table A22 as long as our working fluid was air. If we're using a constant specific heat analysis, then we'll never find the individual specific enthalpies. Instead, we'll make the assumption that delta H is approximately equal to the specific heat at constant pressure, or CP, times T2S minus T1, or some other delta T. How do we find the temperature at the exit of the isentropic compressor or turbine? What we do is we look under our isentropic relationships for ideal gas for an equation that has Cp, Cv, or K, which is Cp divided by Cv. In this case, the equations we're looking for have K in the exponent, and again, we'll typically know pressure ratios instead of volume ratios, so we'll use an expression that looks like this to find the temperature at the outlet of an isentropic process. We did a brief example last class where we went through a four-component ideal Brayton cycle, and we found that the net power in that case was 520.7 kilojoules per kilogram, and we had a thermal efficiency of 44.8 through this ideal cycle. So now you may be asking, can we improve this thermal efficiency? So that's what we're going to look at today. What are some strategies we can use to improve thermal efficiency of Brayton cycles? It turns out that increasing thermal efficiency improves economic outcomes, but also environmental outcomes. So this is kind of a win-win situation when we can do this. Like a Rankine cycle, we'll use regeneration, which is a method of preheating fluid that's going into our combustor or our heat addition process, or we'll use reheat, which means that we'll split our turbine into two different turbines, a high pressure and low pressure turbine, and we'll heat in between. But we'll also use a strategy that we didn't use in Rankine cycles, and that's called intercooling. Intercooling is like reheating, but this happens on the compressor side. So here we'll split our compressor into a low pressure compressor and a high pressure compressor, and we'll cool the fluid in between. And that'll make it a little bit easier to compress our working fluid. So regeneration in Brayton cycles means we'll take some of the heat that we normally would have exhausted out to the atmosphere, and we'll try to use it to preheat the fluid that goes into the combustor. A setup like this might look something like this picture here, where normally, without this regenerator, we would have the compressor going right into the combustor, and we'd have this turbine outlet be the exhaust. But in this case, we're taking this exhaust heat from a turbine, running it through this regenerator on the hot side, and on the cold side, the high pressure air from the compressor goes through the cold side of the regenerator and heats up. So it's going to take some of the heat from this exhaust. So this is good on two fronts. First, we reduce the amount of natural gas that we have to burn in order to get to our desired temperature. But second, we're also going to reduce our exhaust temperature here, which is good for the environment. So here in the textbook, we had this animation where we see our hot fluid coming out of the turbine, our cold fluid coming out of the compressor, and they pass by each other and they transfer heat. In some homes, if they're maybe Energy Star rated, you'll also have a system like this where in the wintertime, you're spending money to heat the air in your house, but if it passes through a heat exchanger where you're bringing air into the house that's cold because it's cold outside, you can preheat that air. You can do the same thing in the summer when your air conditioner is running, where you're blowing out exhaust from your house, which is cold air, and it can pass hot air as it comes in to kind of pre-cool that coming in. So how does a regenerator work? When we draw this on a TS diagram, normally we would add heat from state 2 to state 3. So without the regenerator, we have to add enough heat to go all the way from state 2 to state 3. If we used the equation for the first law that we normally use, we would get that Q dot in divided by M dot would be H3 minus H2, or H out minus H in. But we'd like to add less heat. And the cool thing here is when we use this exhaust gas coming out at 4 and cooling down to Y, we can increase our enthalpy going into our combustor up to this state X. So here we're preheating that fluid before it goes into the combustor, which means we add less heat by burning natural gas. Now, this is a little bit like an oven, right? So here we're going to reduce the enthalpy that we put in the combustor because now we only have to go from X to 3 instead of from 2 to 3. But this is a little bit like an oven. So if you put something into the oven, it can only heat up to the temperature of the oven. You can't add any more heat after that. So our maximum temperature that can come out of the regenerator is the maximum temperature here, which is the exhaust temperature of the turbine. So I can't increase this temperature at X past state 4. And actually, usually I don't exactly get to state 4 either. So we talk about regenerators. We have an efficiency for that, right? In thermal, we've got an efficiency for everything, and they all mean different specific things, right? So here, if we look at the regenerator up in the corner here, right, we'll zoom in on this. And here, on one half of our heat exchanger, we're going from state 2 to state X. But on the other half, we have an inlet of 4, and it's cooling down to state Y. So our regenerator efficiency, right? So the heat that we're adding in the regenerator is the heat that's transferred from the exhaust to this mass that's going into our combustor. So we want to talk about that regenerator efficiency. It's going to be the actual amount of heat that we transfer divided by the maximum that we could. So the maximum amount of heat transfer we could have in this case was if we went from this temperature at 2 all the way up to the temperature at 4. I don't recommend doing this, but if you have like one of those McCain frozen pizzas or something and you put it into your oven, let's say you're cooking it at, 375 or something, if you left it in there all night, let's say, it would burn, right? It would become 375 degrees and you'd have a ruined pizza, right? So in this case, our maximum temperature that we can get is the same thing. So this maximum temperature at 2 could go all the way up to 4. But typically we have some regenerator efficiency that stops us not just from getting to that maximum temperature, but stops us somewhere below that temperature, right? So we know that Hx has to be less than or equal to H4. So the maximum amount of heat that we can transfer would be if we went from the temperature at 2 all the way up to the temperature at 4, right? And if the temperature at X was 4, then it's like the temperature of X max is the temperature at 4, and the enthalpy of X max is the same as the enthalpy at 4. So our actual heat transfer is going to be H out minus H in. So that's Hx minus H2, right? So the outlet of this side minus the inlet of this side. But the maximum would be if the outlet of this cold side of our heat exchanger was the same as the inlet. So our maximum heat transfer rate here is H4 minus H2. And if we use this equation, this gives us our regenerator efficiency. So oftentimes a problem will either ask us what's the regenerator efficiency or tell us what the regenerator efficiency is. Typically, regenerator efficiencies, just because of the way that heat exchangers work, run between 60 to 80%. So we usually don't get all the way up to T4, but we're still reducing the amount of heat that we have to put in. We can also use the same reheat strategy that we used in a Rankine cycle. So here we split off our one turbine into two different turbines. We have a high pressure turbine and a low pressure turbine, and in between we reheat the working fluid. So if we're drawing this on a TS diagram, it looks the same as it did in a Rankine cycle, although we don't have a vapor dome in the middle of our cycle here. The turbine part looks the same. So we go through this first isentropic turbine, then we add some more heat, and then we go through this second isentropic turbine. So now, if we remember that the area in my cycle, if these are isentropic processes, is equal to the net heat, which is equal to the net work, what I've done is I've added this little bit of area over here, this kind of little bleb over here that I've circled in kind of this blue color, and that's an increase in the net power. So the net power here is increasing faster than the heat in, and that improves our thermal efficiency, just like it did in a Rankine cycle. So here's the cool thing. When we use reheat and regeneration together, they kind of work together to make the whole process better. If we have a temperature or a cycle without reheat, we have this exhaust temperature 4 prime. But when we do reheat, we have a higher exhaust temperature. But when we use regeneration, right, remember, as our regenerator can get us close to our exhaust temperature, so as we increase the exhaust temperature, that means we can preheat this fluid more than we would if we didn't have reheat, which maybe means that we're putting in less heat as we go through the combustor, right? So this higher exhaust temperature means that we're reducing, we can scavenge more heat from this exhaust, and that reduces the amount of heat that we put in. Here, this is just a little picture, right? So without regeneration, we're moving from 3 to 4 prime, and our regenerator can, at the best case, get us to 4 prime, right? And then we have to add heat to go from 4 prime all the way to 3. But if we use reheat, in the best situation now, we could get all the way up to this temperature 4. And now, in our combustor, we'd only have to go from state 4 up to state 3. So we'd add less heat. Right? In the business world, right, they call this synergy. This is one of those buzzwords that you hear a lot in the business world. Synergy basically means when you do two things and you basically get more benefit than you would get from doing either by itself. So it's kind of like it doesn't work mathematically, but when you say synergy, you're basically saying something like 1 + 1 is equal to 3, or at least something more than 2. So the other strategy that I talked about that we could use here is called intercooling. Now, intercooling is a little bit like reheating, except that we're doing it on the compression side. So we go from having one compressor to having two compressors. Now, we never did this in Rankine cycles because in Rankine cycles, it didn't take us much power on our pump side. So the idea of reducing the amount of pump power we had to put into the system didn't really make that much sense when our backwork ratios were only on the order of 1% or lower. But here in our Brayton cycle, where our backwork ratios can be, upwards of 20%, having this strategy to reduce the power that we put in to get up to that high pressure makes sense. So what happens is, as we go through this first compressor, we're compressing the fluid, but it's also heating up, right? And if you remember, as fluids heat up, there's more vibration in those molecules, and the molecules themselves want to space out as they get hotter. So what we do here is we cool the fluid here from state C to state D. And as we cool that fluid, those molecules are vibrating less, right? They have less Brownian motion. So it's easier to then compress them together. We can do that with less power. So using this intercooling reduces the power into the system, which improves or increases our net power generated by the cycle. So I couldn't find a picture of this in the textbook, so I kind of drew this little bleb by myself over here, where reheat adds this area to our network. Intercooling adds area to our network by reducing the amount of power that we put in. So here we're cooling between state C and state D, and that lets us get up to the pressure that we want with less power. Right? So our network increase happens because we're adding this little bleb on the left over here. Intercooling reduces the total compressor power, and that has the effect of increasing our net power of the cycle. So now that we've kind of introduced these ideas, I want to show you how we would go about solving a big Brayton cycle problem here, right? So this is kind of a Brayton cycle with all the trimmings, even though it's not Thanksgiving. Right? So here we're using intercooling between two compressors. We're using reheat between two turbines, and we have regeneration. We're told the efficiency of all the compressors, all the turbines, and the regenerator is 80%. We're given the mass flow rate. We're told the compressor pressure ratios as we move through the system. First, that the total compressor pressure ratio from 1 to 4, so that's across both compressors, is 10, and that the individual compressor ratios are the same. So here we have to have this ratio times this ratio equal to 10. So this is going to be the square root of 10. We're told the temperature and the pressure at the inlet along with the mass flow rate, and we're given some other temperatures along the way. We also are told the pressure ratios as we come down through the turbines. So our state table looks pretty bleak here, right? And it also looks like it has a lot of states. If you just look at the numbers, you might think that there's 10 states, but really we're doubling up on a bunch of states here because we'll have the isentropic and real outlets of the turbines and the compressors, right? So really we have, I think, 14 states here to fix. And we're only really given temperature and pressure at one of these states, and then we're given a couple of temperatures spread out through the system. So this is basically from question 9.81 in the textbook. So first, I want to draw the TS diagram. Now the TS diagrams here are a bit of a bear because there's so many states. But I know that the minimum temperature in my cycle is 300 degrees. I also know that there's going to be 3 pressures. So there's some low pressure, which is about atmospheric pressure. So my first state comes in at 300 degrees and 100 kilopascals. I know that state 3 is also 300 degrees. But to get there, first I want to compress to some intermediate pressure. So I'm going to have an isentropic compression and then my intercooling. Then I know that my high pressure is 10 times what my low pressure is. So this is going to be 1,000 kPa. So I can find the maximum temperature here, I'm told, is 1,400 Kelvin. So I know that that's my state 6 at that high pressure and the high temperature. And I know to get from state 3 to state 6, first I go through this compressor. If it was isentropic, I would get to 4S. There's going to be some intercooling going on somewhere in here. I don't know where to put state 5 yet, but it's somewhere along this line. And then I come up to state 6. From state 6 to state 7S, I go through an isentropic turbine. And then I do my reheat all the way back up to the same maximum temperature that I had at 6. So that gets me to state 7S and state 8. I come back down through my low pressure turbine. That gets me to state 9S. And then here, even though there's not a component that goes all the way from 9S to 1, I'm going to draw this as one line, even though part of this cooling just happens in the environment. So now I also have that this state 5, right? Remember our regenerator is going to go from state 4S up to state 5, right? And I know that the temperature at 5 has to be less than this exhaust temperature at 9. So here, I'm going to draw state 5 over here, and then I also need to add my exhaust, right? So this is going to be, this regenerator is also cooling down my exhaust as I go from state 9 down to state 10. So this is what the TS diagram would look like if all my processes were isentropic, but they're not. So I have to put on the real states, so the real compressor outlet, the real second compressor outlet, the real first turbine outlet, and the real second turbine outlet. So drawing these diagrams can be pretty tricky, but I think we know that there are 3 pressures. We go through one compressor, then we cool, then a second compressor. Then we go all the way up to the turbine. The first turbine comes out, then we reheat, then the second turbine. Now we remember that in the regenerator, we're cooling down the exhaust and we're heating up the air before it goes into the combustor. So that's our TS diagram. Now, I can do a first law analysis on all the different components in my system, picking the right assumptions from this list. Right? Remember, the regenerator is going to be both adiabatic and passive. If I want to find my thermal efficiency, I know that it's the net power divided by the heat transfer in. Here, the textbook would tell me that I take the magnitude of the turbine power plus the magnitude of the second turbine power minus the magnitude of the compressor power minus the magnitude of the second compressor power, and then I divide by both the places where I'm adding heat. Because remember, I have reheat here. Right? If we were using the first law, we could just make all of these H in minus H out on the top and let the first law worry about the signs. So that's what we're basically doing here. Right? So now we have an expression for thermal efficiency that's a function of only these enthalpies. If I was doing a cold air standard analysis, which I'll go through today, although we won't actually find the numbers, I'll just go through the process. I pull out CP on both the numerator and the denominator because all of these are delta H's, and I can approximate delta H as CP times delta T. My specific heats are going to cancel, and I'll be left with an equation that's only temperatures. So if I'm doing an air standard analysis with variable specific heat, I have an equation that's only enthalpies. But if I'm doing a cold air standard analysis, then I have an equation that's only temperatures. If I want to find the backwork ratio, now I'm taking the power of all the pumps and dividing by the power of all the turbines. I'll take this as an absolute value. So I take the compressor powers and I divide them by the turbine powers, remembering that the power plant is the first consumer of the power generated by the power plant. So here again, if I'm doing a variable specific heat analysis, I have this as a function of enthalpies. But if I'm doing a constant specific heat analysis, I can pull out the CP from the numerator and the denominator, cancel it out, and I only need to find all the temperatures. Right? Unfortunately, I don't know any of the temperatures right now, except a couple. I know state 1, state 3, state 6, and state 8. But there's a lot of information on this table that I don't know. So how do I go through and fix the states? Ultimately, this comes down to asking myself, what's the fluid? I know that it's an ideal gas. Now, when we have an ideal gas and we're working in a cycle, my argument is going to be always look for the isentropic processes, because when you find an isentropic process, that means you can use an isentropic relationship. Since we're going to be doing this problem as variable specific heat and constant specific heat, I'll show you how to use both of those types of isentropic relationships. I don't need all the states on my state table in order to find my solution. I didn't have H2S on any of the equations that I was looking for, but I need to find the isentropic outlets before I can find the real outlets. So let's go through this process. Right? So if I was doing an air standard analysis, what I would do is take the places where I know the temperatures, and then I'd use the temperatures to find H on table A22. If I was doing a cold air standard analysis with constant specific heat, then I wouldn't care what the individual enthalpies are because I only need the temperatures. So I know state 1, or at least I can look up all the information that I need. And remember, I would look up PR in this case on table A22 as well, even though I don't have that here on my state table. I could do the same with state 3, where either I know the information that I need if it's cold air standard, or I could easily find it on table A22. I can do the same on state 6 and on state 8. So these places where we're only given the temperature, this is not so great if the working fluid was water, but if the working fluid is an ideal gas, just knowing temperature is not necessarily all that bad a place to be. Next, I'm going to look for isentropic processes. Now, there's no reason to pick necessarily which one you're going to look at, but I like to start at 1, which in this case is also the state where we know the most information, and I'm going to just work my way through. So here, from 1 to 2s is an isentropic process. So it's an ideal gas with an isentropic process. So I'm going to go to my equation sheet, and I'm going to look for isentropic relationships for ideal gases. I'll see that there are different relationships if it's variable specific heat or an air standard, or constant specific heat or a cold air standard analysis. So if it's air standard, then delta H is actually going to be delta H, but I need to find H of 2s. So to do that, I use this relationship that P1 over P2s is equal to the reduced P1 divided by the reduced P2. Now, PR1 and PR2 are on my table. So when I looked up state 1, I would pick off PR1 from the table. Maybe I'd have to interpolate. I know my compressor pressure ratio across this first compressor, so then the only thing I don't know here is PR2. When I know PR2, then I can go back and interpolate to find H2S, and I can find T2S. So here the key is to use this isentropic relationship to find PR2, and then use PR2 to interpolate to find H and the temperature. I'd get that from A22, provided that my ideal gas is air. If I was doing a cold air standard analysis, I would never care what delta H is because I'm going to approximate that as Cp times delta T, but I still need to find what the isentropic temperature at the outlet of this isentropic compressor is. To do that, I'm going to look for an equation that has K in the exponent. And in this case, because it's an open system and I know the compressor pressure ratio, I'm going to use this equation. This is the one that I'll usually use when I'm doing open systems. In this case, I know T1, I know this compressor pressure ratio, I don't know T2S. So I can put this number, these information into my calculator and find T2S, knowing that K for air is 1.4. Or if I didn't know that, I could look up Cp and Cv and find K as Cp divided by Cv. So now I know state 2s. How do I go from state 2s to state 2? I use the isentropic efficiency of the compressor, which was given in the problem. So to use the isentropic efficiency across the compressor, we remember that the power of the ideal compressor is divided by the power of the real compressor. If we make the assumptions that we usually make, we can find this as a function of the specific enthalpies across the ideal compressor on the top and the real compressor on the bottom. And that's great if I'm doing a variable specific heat analysis. If I'm doing a constant specific heat analysis, then I pull specific heat out from the numerator and the denominator, and I'm left with an equation that's a function only of the temperatures. Next, I'm going to look at the isentropic process between state 3 and state 4. Now, this is my second compressor, so I ultimately do state 4s and state 4 in the same way that I did state 2s and state 2. So first, I'm going to find the isentropic outlet of this second compressor. I remember that I'm using an ideal gas and I want to use these isentropic relationships. So if it's variable specific heat, I want to find delta H, but I don't know H4s. I need to use my isentropic relationship for variable specific heat. In this case, I know the compressor pressure ratio, so I use the ratio of pressures is equal to the ratio of reduced pressures. I'm going to use table A22 to find PR4, and then I'm going to interpolate to find H4s and T4s. I get that all from table A22. For a cold air standard, again, I'm going to use Cp delta T, but I don't know T4s. To get T4s, I'm going to look for an expression that has a pressure ratio in it and has K in the exponent. So I'll use this equation, At this point, I know T3, and I know the compressor pressure ratio across this second compressor, and I know K. So I can find T4S. So now, again, I'm going to use the isentropic efficiency to find the real outlet of the compressor. Here again, I use my compressor efficiency. If I'm using a variable specific heat analysis, then I use this with the specific enthalpies. But if not, I use the ratio of the temperature differences across the ideal compressor and the real compressor. Next, I get to the regenerator. How do I solve state 5? I can use the regenerator efficiency. So now the regenerator efficiency is the actual amount of heat that I transfer across my regenerator divided by the heat transfer rate that the maximum regeneration would give me. So here I get the actual regeneration is m dot times H5 minus H4 divided by m dot times H9, that's the exhaust from the second turbine, minus H4. So here our maximum heat transfer rate is going to be determined by the enthalpy at the exit of the compressor and the enthalpy at the exit of the second turbine. Because remember, that's like our oven temperature, and that's the highest temperature we can heat up to. The mass flow rates are the same because we haven't split the mass like we did in Rankine regeneration, so I get a ratio of enthalpies here. If I'm doing a constant specific heat analysis, I can get this as a ratio of temperatures by pulling out Cp from the numerator and the denominator. Unfortunately, at this point, I don't yet have the information for state 9, so I'm hoping that I'll be able to find that as I move through the problem. But once I have that temperature, I'm ready to find the next point on my cycle. And that's why we're given the temperature at state 6. So it's okay that I haven't found state 5 yet, because I can start again at state 6, and then hopefully once I find state 9, I can figure out what's going on here at state 5. So my next isentropic process, right? If I get lost on one of these cycles that uses ideal gas, look for the next isentropic process. So that's what I do here as I move through my first turbine. This is similar to moving through the compressors, where we'll have a variable specific heat analysis where we're trying to find delta H, but we don't know H7S, so we can use the ratio of pressures is equal to the ratio of the reduced pressures. Here, I would have found PR6 when I fixed state 6, given that maximum temperature. So now I can find PR7 from this equation and interpolate backwards to find H7S and T7S. I get that information again from table A22. If I'm doing a cold air standard analysis, I'll say that delta H is equal to Cp times delta T. I don't know H7S, but to get it, I look for an expression that has K in the exponent, because that'll tell me how to deal with isentropic processes for ideal gases. And because this is an open system, I'm going to know the pressure ratios, so I can use this expression to find T7S. When I have T7S, I can use the isentropic efficiency of the turbine to find H7 or T7. So now I know that the real turbine produces less power than the ideal turbine. So now my turbine efficiency is the real power divided by the ideal power. I can simplify that to a function of specific enthalpies. I can use the cold air standard analysis to then further simplify that to a function of only the temperatures. So that will give me the temperature at the real outlet of the turbine. So now I look for the second turbine, and I'll try to do the same process. First, I'll look for the isentropic process to find 9S. Again, I can do this as an air standard or a cold air standard process. If it's air standard, I'll actually get the change in the enthalpies. I'll find each individual enthalpy. But in order to get H9S, I have to use the fact that I know the pressure ratios across the turbine, as the pressures here is decreasing. I know PR8 because I fixed state 8 already, and this will give me PR9S. And when I have PR9S, I can interpolate back and find H9S and T9s using table A22. In my cold air standard analysis, again, I don't ever find the individual enthalpies. I just get the difference by approximating that as Cp times delta T, but I don't know T9s yet. So to find T9s, I use this expression that's got K in the exponent. Again, I'm making use of the fact that I know the pressure ratio across this second turbine. I put that into my equation and I get T9s. But what I really want in my equations for thermal efficiency or for backwork ratio or for net power is T9 or H9. So I have to use the isentropic efficiency to find what's going on at the real turbine exit. I use the same turbine equation that I used before, that my isentropic efficiency here is the real turbine power divided by the ideal turbine power, remembering that the ideal turbine generates more power than the real turbine. I can get a function of specific enthalpies, or I can use a cold air standard analysis to get this as a function of only temperatures. Now, the only temperature I don't know in this case is T9, or if I'm doing an air standard analysis with variable specific heat, the only thing I don't know is H9. So I can use the turbine efficiency to find either T9 or H9. And now remember, we needed to find state 9 in order to fix state 5. So now that we find state 9, we can go back to state 5. And at state 5, when we did the regenerator efficiency, we were left with this equation, which was one equation with two unknowns because we didn't know H5 or H9, or we didn't know T5 and T9 if we were doing a cold air standard analysis. But now that we've moved through the rest of the cycle, we've found H9 and T9, so we can go back and use this regenerator efficiency to find the temperature at state 5. So now we're almost done, right? We've found states 1, state 2s, state 2, state 3, state 4s, state 4, state 5, state 6, state 7s, state 7, state 8, state 9s, and state 9. Right? The only one that we haven't found is state 10. And in order to find state 10, we have to do the first law on the one component that we haven't touched yet. We haven't done a first law analysis on the whole regenerator, even though we did use regenerator efficiency to fix state 5. So if we look across the whole regenerator, then we can say that it's steady state, there's no change in kinetic energy, no change in potential energy, that it's adiabatic and it's passive, that there's no friction losses, so that the pressure is not dropping on either side, and that there's no heat loss, meaning that all the heat from the hot side, from that exhaust gas that gets lost, goes into the preheating of the fluid that's going into the combustor. Now, if we do that, we'll get that for the regenerator, we get the sum of m dot in H in minus the sum of m dot out H out is equal to 0. Here, our inlet terms happen at state 4 and state 9, which we've fixed. Our outlet states are state 5 and state 10. We've fixed state 5, but state 10 we don't know. So I can group these things by the side of the heat exchanger that they're on. I can see that the mass flow rates on both sides of the heat exchanger are the same. So this is one of the things that's maybe a little bit easier about this Brayton cycle. Even though there's so many states to fix, we don't split the mass. So it's a little bit different than when we do regeneration in a Rankine cycle. So here the mass flow rates are both the same. So they come out here. And the only thing that I don't know is H10. So if this was a variable heat analysis, what I would do is isolate for H10, and I'd find that it's a function of H4, H5, and H9, which I've already found. If this was a constant heat analysis, then from this equation here, I would use my Cp delta T equation, and then I would divide Cp on both sides, and I'd isolate for T10 and find that it's a function of T4, T5, and T9. So I know that it's been a bit of a slog to go through all of these states. But essentially, what we did was just march through our state table looking for isentropic processes And then in cases where we didn't have isentropic processes, we tried to use information about the regenerator, whether it was the regenerator efficiency to find state 5, or in this case, the first law across the whole regenerator in order to find state 10. So hopefully you get some idea of how to do this. I know we didn't find numerical answers, but I tried to go through the process for constant and variable specific heat. So hopefully when you're looking at this, you can see how to take either one of those two paths through this kind of Brayton cycle with all the trimmings. So we're not quite done with Brayton cycles, but we're done with Braytons as a power plant. Our next couple of lectures will be about trying to use a Brayton cycle at the heart of a turbojet engine. So in our next couple of classes, we'll wrestle with the question, what do we need to fly? I'll see you next time on Thermodynamics.